Hello, my name is William Stafford from the Natural Resources and Environment Unit of the CSIR. Today I'm going to be talking to you about sustainability science and systems thinking. This presentation is structured into different sections to allow you to pause, discuss and reflect on each section as you proceed. So firstly, why do we need sustainability science and systems thinking? Well, there are increasing demands on the Earth, and we are currently facing what's known as an ecological crisis. So the population between now and 2050 is expected to increase from 6.9 billion to more than 9 billion, and with most of this growth occurring in the developing world. As a result of this population growth, there's a pressure on the natural resource base and the resultant overexploitation and resource depletion. This incurs biodiversity loss, pollution and climate change. The greenhouse gases are projected to increase by 52% in the year 2050. The impacts of this climate change will be increased heat waves, droughts, storms and floods, which results in severe damage to key infrastructure and crops. These are the warning signs. The system can no longer sustain itself. So our current developmental model, the business as usual approach, is not a sustainable option. To summarize, the combined stream of economic, social and environmental crises that have plagued the global economy in recent years points to a need to reorient the current developmental models towards a more efficient, inclusive and sustainable economy by enhancing the resource efficiency of national economies and decoupling economic activity from environmental degradation. Essentially, for sustainable development, we need to think about how we can grow sustainably without depleting our natural resource base on which our very dependence resides. Essentially, for sustainable development, we need to increase human well-being, increase human economic activity while reducing resource use and reducing environmental impact. In other words, for any successful sustainable developmental model, we need to incorporate both resource decoupling as well as impact decoupling. If we make the analogy between economics and ecology, we can see that in terms of economics, we have an endowment or an investment that generates interest. If the withdrawals exceed the interest generated, we'll incur a debt in the system, and this will subsequently erode the value of the endowment. Similarly, in the ecological sense, the interest we receive are the ecosystem services derived from nature. Nature, in terms of the global ecosystem, delivers a whole range of valuable ecosystem services, such as clean air, clean water, and pollination services, to name a few. This is in addition to the whole range of natural resource products that can be generated from nature. What's important to consider is that our withdrawal or our ecological footprint should not exceed the ecosystem services that can be delivered from nature. However, currently this is not the case. Our ecological footprint is approximately 1.5 times the ecosystem services that are delivered by nature. So currently, our ecological footprint is about 1.5 Earths. If we continue on this business as usual approach, by 2050, our ecological footprint will be 2.3 Earths. Clearly, this is not sustainable. And for a sustainable development vision by 2050, we would need to reduce our ecological footprint to maintain ourselves within the carrying capacity of the Earth, i.e. approximately 1 Earth. So what is sustainability? Sustainability is improving the quality of life while living within the carrying capacity of the world's ecosystems. In addition to living within the ecological limits, sustainability is also about how these ecological products and services are shared. In other words, how the world's natural resources and wealth are shared between different individuals. Sustainability is about meeting the needs of the present without compromising the ability of future generations to meet their own needs. So, for sustainability, we need to think about both the intergenerational and the intergenerational equity. In terms of the intergenerational equity, this is the sharing of wealth and resources between different individuals or countries of the same generation. So if you think about your country of interest, some individuals may have vastly greater consumption patterns and have accumulated much greater wealth compared to others. The inequality in the society, or the distribution of wealth, i.e., the difference between the richest and the poorest, can be measured by the Gini coefficient. Countries such as South Africa and Brazil have some of the highest Gini coefficients in the world, and that means they're some of the most inequitable regions in the world in terms of the distribution of wealth. In addition to the sharing of wealth and resources within people of a given country, we also need to consider the sharing of wealth globally. In this picture of the 2003 World Consumption Cartogram, countries have been stretched to indicate their effective consumption. You'll see that countries with high levels of consumption are a lot larger than they actually are in the physical sense, in contrast to other countries which have low levels of consumption, which appear shrunk compared to what they physically are. This clearly depicts the fact that some countries have consumed vastly more resources than others and are utilizing a lot more of the natural resource base and wealth compared to other countries. However, what's also very interesting is that these countries, which have high consumption patterns, are largely also countries that have incurred huge ecological deficits. And this is simply a result of the fact that these countries have developed in a way that has overexploited their natural resource base. And this has resulted in considerable ecological deficit, shown here in the countries in red. So in addition to this intra-generational equity described, either on the country level or globally, we also need to consider the intergenerational equity. In other words, what kind of a world do we want to leave to our children? Or what kind of a world will our children inherit? Will it be a sustainable one? So these are some of the current challenges that we face today, and some of the big questions that we need to answer, such as, how can we meet the world's growing needs while remaining within the Earth's carrying capacity? This graph shows the Human Development Index on the x-axis and the ecological footprint on the y-axis. The Human Development Index is a composite measure consisting of life expectancy, education, and GDP per capita. You'll immediately see that many developing countries, such as those of Africa, have a relatively low Human Development Index, or HDI, compared to several other developed countries. However, many of these developed countries also have a huge ecological footprint. So their improved HDI has come at a significant ecological cost. Their ecological footprint is typically way above the world average biocapacity available per region. The bottom line is, if developing countries are to develop more sustainably, they cannot simply follow the same trajectory that developed countries have. They essentially need to move into this quadrant, where they improve their HDI while maintaining a relatively low ecological footprint. So we live in this complex, interconnected world, where the Earth's systems are linked to human activity, and human activity is linked to biogeochemical cycles and climate change. Therefore, to conceptualize and think about these huge global systems, which have enormous complexity, and big questions like, how can we meet the world's growing needs while remaining within the Earth's carrying capacity, are very challenging. These questions are complex because they have many influences and many different actors. They're also wicked problems because they have several different causes. They also have many different divergent viewpoints and occur in multi-scales, from the local to the global scales. And lastly, these issues and actions change over time. They're dynamic. Therefore, we somehow need new ways of thinking. In the words of Albert Einstein, the significant problems we face today cannot be solved at the same level of thinking at which they were created. So what exactly is systems thinking? Systems thinking is a framework for seeing the whole picture with interrelationships. It's also a framework for seeing the patterns of change rather than static snapshots. Systems thinking requires us to understand that while there is only one Earth, it is composed of a multitude of subsystems, all interacting with each other. So what is systems thinking exactly? Well, a more formal definition is systems thinking is utilizing modal elements to consider the componential, relational, contextual, and dynamic elements of the system of interest. Sounds a bit confusing, and it'll become clearer as we progress through the course. But the system of interest that we're studying, we need to think about the components of that system, their relation to one another, how those components and their relationship changes depending on the context, and how it also changes depending on time. So when we want to carry out systems thinking, we need to think about the interactions of the system and a chain of cause and effect that describes the overall system's behavior. We should focus on patterns of change over time, rather than on isolated events, and this will lead to rich discussions on how and why something is changing. So what exactly is this thing called a system? Well, a system simply is a collection of things with a definable boundary that have some sort of relationship to each other. Therefore, systems consist of a complex web of relationships between parts of a unified whole. The importance of each component of a system is essentially tied to its relationship to the whole. And lastly, the essential properties of a system are properties of the whole. Many properties of the system are emergent and cannot be ascribed or described by individual components of that system. So if we compare the classical or traditional mechanistic view to this new systems thinking view, we come up with some interesting observations. In the mechanistic view, the universe is considered a machine, while in the systems view, the universe is considered as a complex system. In the mechanistic view, we often apply an analytic method, applying reductionism, isolating components into their individual parts and studying them. In contrast, in the systems thinking approach, we study structure and organization, and we look at the interdependent relationships of the parts to reveal emergent properties of the whole system. Again, in contrast to the mechanistic view, where there is only one correct perspective based on the facts, the systems thinking view considers different perspectives with both hard and soft facts. And lastly, but importantly, the mechanistic view thinks in a predictable linear cause and effect manner, whereas the systems view thinks of cycles of cause and effect, i.e. feedback, and also dynamic complexity, how the complexity changes over time. So why then is systems thinking not a natural act if it is so important for our evolution? Well, it seems that human evolution has favored mechanisms tuned to dealing with immediate surface features of problems and not big global complex issues. Additionally, our educational approach has definitely favored a mechanistic reductionism approach in both research and decision making. Lastly, the complexity of systems thinking often overwhelms our cognitive abilities because we are bounded by rationality, and yet systems thinking demands that we think about predictably irrational behavior. In addition, comparing different attributes or criteria simultaneously is challenging in the cognitive sense. Some people believe that approximately no more than 7 different criteria can be perceived in the human mind at any given time. So the complexity causes huge challenges in terms of our cognitive abilities. So if we apply systems thinking, what are the likely benefits? Well, essentially the power of systems thinking comes from a focus on systemic structures, or the actual patterns of behavior, and this will offer new opportunities for integration as well as management control. In addition, a systems approach can help shed new light on current problems, viewing them from different perspectives that can prevent many unexpected or unwanted results. Further, systems thinking often offers a range of tools for gaining deeper insight into problems. And lastly, systems thinking demands that we include social, political, natural, and economic aspects into an integrated view in order to facilitate sustainable development. So having discussed what system thinking is and what a system is, now we'll explore how to look at the different system interactions and how we define the system boundaries. So what we're considering in our system is the socio-ecological interface. It's clear from our discussion so far that climate interacts with the biosphere and maintains biosphere integrity, as well as the production of ecosystem goods and services. The climate interacts with the biosphere through biogeochemical cycles, such as the carbon cycle and the water cycle. These are what's known as the ecological elements of the system. In addition, there are numerous social elements of the system, because humans interact with the biosphere and derive ecosystem goods and services. So we need to think about human consumption per capita, population, as well as a host of other social factors, such as equity, needs, values, and ethics. So in terms of extraction and use, the impacts of human activity essentially link both the water and carbon cycles. For example, land use changes and fossil fuel use result in the exchange of soil moisture to atmosphere, as well as the emission of carbon dioxide to the atmosphere. So these anthropogenic impacts will essentially help to link the water cycle and the carbon cycle. And lastly, we're fully aware that both the water cycle and the carbon cycle regulate the Earth's climate. So human activity and the future of life on Earth will be dependent on the regulation of these biogeochemical cycles, which can only be maintained through correct management or the human ecological interface. So these socio-ecological systems are very complex. There are multiple ecological impacts from climate change. For example, in this diagram we can see that climate change causes certain urban climate changes, such as changes in precipitation, warming, and sea level rises. And this results in a range of different impacts, including building subsidence, water scarcity, deteriorated water quality, changes in air quality. However, adaptations to these challenges, or this climate change, can cause added impacts, and these can best be described as fixes that fail. So for example, adaptations or mitigation measures to some of these urban climate change impacts might be cooling, water treatment, long-distance water transfers, pump drainage, and groundwater mining. These adaptations can in turn result in an increase in greenhouse gas emissions that further exacerbates or increases climate change. Therefore, these socio-ecological systems are extremely complex. They involve many different interactions that occur at different spatial scales. And these interactions change over time. So if we consider a basic water resource, such as Lake Mendota, considered in my earlier presentation, we realize that this lake resource obviously has an inflow and an outflow of water. It also, of course, interacts with the atmosphere and interacts with the groundwater in terms of the evaporation, precipitation, groundwater inputs, and seepage. So the boundaries of the system would clearly be classified in a hydrological sense as the river basin or the hydrological boundary. However, what we see, apart from the fact that Lake Mendota is linked to the atmosphere and hence climate and climate change, the water resource is clearly governed by a whole range of different human activities, which aren't shown here. In addition, human population and activities are in turn influenced by climate change. Therefore, there's multiple levels of feedback in the system and includes a range of human activities that aren't featured here. In essence, the system boundary of Lake Mendota is wider than the pure biophysical hydrological boundary. It needs to include a whole range of different issues and actors as part of the socio-ecological system. So in summary, we have discussed why we need sustainability science and systems thinking. What is systems thinking? what is a system and how to define its boundaries. So in summary, the current world crisis is leaving little choice but to transition to a more sustainable world. The world's problems are complex, interrelated, and occur at multiple scales, from the local to the global. Therefore, new approaches, such as systems thinking, are needed to understand this complexity. Systems consist of a complex web of relationships between parts of a unified whole. The importance of each component of a system is tied to its relationship to the whole. And the essential properties of a system are the properties of the whole. Many of these are emergent properties and cannot be ascribed to any individual component. Therefore, systems thinking focuses on these system interactions, the patterns of behavior, and how these patterns change over time. Thank you very much for your attention. Please answer the questions and respond by blogging on Moodle.